Alright, so the dimensional analysis that problem 1.39 is asking us to do is we're going to look at some constants of nature. We have G, which is the gravitational constant, which is 6.67 times 10 to the negative 11th meters cubed per kilograms second squared. We want to know what dimensions G has. So meters has dimensions of length cubed. Downstairs we have kilograms, which is dimensions of mass to the negative 1. And second squared, again downstairs, that's time to the negative 2. So we've got our dimensions for our gravitational constant. And we're going to look at the Planck constant, which is 6.63 times 10 to the negative 34th, getting some small numbers here. Kilograms meters squared over seconds. So kilograms is upstairs, that's M. Meters squared is upstairs, that's L squared. And time to the negative 1. And then in C, our friendly speed of light, 3.00 times 10 to the 8th meters per second, which is a length per time. So we have our dimensions here, and we have our SI units. What the book wants us to calculate is the dimensions of G times H over C cubed. We're going to transform this into G times H over C cubed to the 1/2. So 1/2 and the radical are the same thing. This just lets us use our property of exponents. And so I'm going to place in my dimensions for G, L3, M, negative 1, T, negative 2, and for H, M, L squared, T minus 1, all over LT minus 1. We don't want to forget to cube our speed of light. And we put this whole thing to the 1/2 power. So it's pretty tasty looking dimensional analysis there. So we'll work with the numerator first. I have an L cubed and an L squared, that's L to the 5th. And M to the negative 1 times M to the 1st is 1. So mass is not coming into play here. T to the negative 2 times T to the negative 1 is T to the negative 3. And I'll cube my denominator, so that gives me an L cubed and a T minus 3, all to the 1/2. Using my rule of exponents, that gives me L squared, all to the 1/2. Again, using my rule of exponents, because notice the T to the negative 3 over T to the negative 3 gives you 1. And so anything to the 1/2 power, divide the exponent by 2, or multiply the exponent by 1/2. Same deal. And we get L. So these constants come together to be a length. And specifically, it's a thing called a Planck length, which is the smallest measurable thing in the universe possible. Well, we know what the dimensions are, so let's plug in these numbers to find out what this is. And this might give your calculator some problems. I know it was giving the one on the computer a problem with me here. I want to probably pop something else up to get this. But we'll look at our rules of exponents. So I have 6.67 times 10 to the negative 11th meters cubed kilograms second squared. Now, because we did the dimensional analysis, I'm going to do something that you won't see me do, Thompson. I'm going to drop the units. These are all in SI units, and we just did dimensional analysis. So we know our answer should be in meters. In general, I suggest you keep the units in so they can cancel. But when we look at this problem and what we did in part A, we can say, hey, we're going to get meters out of the other end of this as long as we use SI units. And all of these constants are given in SI units. That's a check we're doing beforehand. Would not recommend this on every problem set until you have 3.00 times 10 to the 8th cubed. All of this to the 1/2 power. We know, so I say always keep your units. Well, we know what's going to come out of that's a meter. So that there, we're not cheating. We're leaving our units out in the end. But we've gone through all the dimensional analysis, so we don't have to keep track of each constant. So let's group some things together. So I'm going to cube 3. So 3 times 3 is 9, times 3 is 27. 3 cubed is 27. And 10 to the 8th cubed, using our law of exponents, is 10 to the 24th. So there's our denominator. Now 10 to the negative 11th, and 10 to the negative 34th is going to give me 10 to the negative 45th. And then I want to multiply 6.63 times 6.67. That's going to be around 40 something. Let me get a calculator out here again. Let's see, we get 6.67, 6.67 times 6.63 equals 44.22221. So 44.2221. All of this to the 1/2. Now I entered all of this into my into the calculator on the computer, and it returned to me 0. This number is so small, the computer couldn't compute it. Now, again, as you've heard me complain twice in the video, if I had my TI-89, I think I could run this through. But we're going to use our law of exponents. So what I want to do is I'm going to turn the bottom into 10 to the 25th by moving one to the right. Make this 10 to the negative 45th over 2.7 times 10 to the 25th, all to the 1/2 meters. I want to subtract my bases, so that's 10 to the negative 70th. And then I'm going to divide 44.22221 by 2.7. Let me get this here. I still have it here. So divide by 2.7. That gives me 16.38. 16.38. 16.38 times 10 to the negative 70th, all to the 1/2 meters. And again, I'm having calculator problems because this number is so small. My calculator says it's close enough to 0, Jeff. Stop complaining about it. So using my law of exponents, 16.38 I want the square root of. So I'll take the square root of this number. That gives me 4.047. Want it to 3 sig figs, so that's 4.05. 4.05, taking the square root of this part. And then my power rule, 1/2 times negative 70 is negative 35. meters. And so the Planck length is 4.05 times 10 to the negative 35 meters. That's as small as we can measure anything in the universe. And the Planck scale is debatable, and there's different theories that suggest different things. But this started off with dimensional analysis, and we had to use our scientific notation to help us because our calculator was not playing well with these large exponents. And you'll get that periodically. You'll get numbers so small or so large that you have to use your rules of exponents to make the scientific notation work.